The results of the Biot-Savart law are wonderful for calculating the magnetic field due to wire segments in three-dimensional space. So you want to keep those results in mind as a superposition of some kind of wire configuration. But also useful, especially mathematically, is Amperes' law. In cases of symmetry, we can use Amperes' law instead of the Biot-Savart law. Amperes' law looks like this. The integral of a magnetic field around a closed path, designated by ds, is proportional to the current enclosed by that path, and the proportionality constant is mu naught, the magnetic permeability of free space. So, in essence, if we were to look at this current here and this current carrying conductor, we know there's a magnetic field going circularly around that current, and if we choose that path, ds, around that current, then B and ds would be in the same direction all the way around that current. All we have to do is integrate that line integral of the magnetic field with every little infinitesimal ds, and that should be proportional to the current that is enclosed within that circle. So it's really a simpler mathematical relationship than, say, dealing with the Biot-Savart law, which had a cross product inside a volume integral. So here we just have a line integral about a closed path is proportional to the current that flows through that closed path. Here's an example. A long straight wire of radius r carries a uniform current I naught that is uniformly distributed through the cross section of this wire. Calculate the magnetic field at a distance r from the center of the wire in the regions where r is greater than the radius of the wire and where r is less than the radius of the wire. We're going to use Amperes' law to do this. So we have a current I naught going through this wire, and we're going to consider some radius smaller than the radius of the wire itself, and that is going to be our path, is around that circumference of that circle of radius r. Hence, we're only going to include and enclose a fractional amount of the total current within that circle. As we consider our line integral, B and ds will be in the same direction all the way around this circle. Hence, B dot ds will be B ds cosine 0. Cosine 0 is 1, so we can simplify our integral to just B ds is equal to mu naught I enclosed. Sounds good? As we go around this circle, it is symmetric around its center, and there's no reason why the magnetic field would be greater at any particular point as opposed to any other point. So the magnetic field, by symmetry, will be constant everywhere around our line integral. Hence, we can take a constant out of the integral, and that's what we're going to do here. So now we have magnetic field times the integral of our ds around this circle is equal to mu naught times I enclosed. Now the I enclosed, though, is just that fractional amount of current that's in that area. It's going to be the fraction of that area to the total area, that amount of the total current available. So our enclosed current is going to be pi little r squared over pi big R squared times I naught, the fractional area. And if we do our line integral around the circle, that's just going to be the circumference of the circle, 2 pi r. So now we have the field times 2 pi r is equal to mu naught pi r squared over pi big R squared, I naught. One of the r's cancel out, and the pi's cancel out, and we have that our magnetic field at a radius r within the wire is equal to mu naught I naught over 2 pi radius of the wire squared times r. R is our variable, everything else is a constant, so the magnetic field is equal to a constant times our variable r. If we were to graph this, it would be a linear function. As r got greater, the magnetic field would get proportionally greater as well, and the magnetic field would be a linear relationship with the radius of the wire, inside the wire. What about outside the wire? If we form our path outside the wire, we're simply going to enclose the total current I naught at whatever radius we have, and so that's going to be our total current enclosed, I naught itself. So now our Ampere's law, everything else being the same, the integral of B dot ds around this big circle is going to be B times 2 pi r equals mu naught I naught. Hence, the magnetic field at some arbitrary radius outside the wire is going to be mu naught I naught over 2 pi r, and that is indeed the magnetic field outside a wire, an infinitely long wire. This is the same result we got from the Biot-Savart law, where we extended the law in the wire segment to infinity on both directions, so that our first angle was 0 and our second angle was 180 degrees, and we ended up with this result as well. So here's a way that we can get it in an easier way using the Ampere's law. Let's try this law out. Here we have two wires. One's carrying a current of 6 amps down, and the other one's carrying a current of 6 amps up. Find the magnetic field at points A and C, where the distance d is equal to 0.7 meters. Our approach to this will be by using superposition. We're going to find the magnetic field due to each wire separately, and then we're going to add those results together. We're going to superimpose them together and get our vector result after that. So assuming we have infinitely long wires, if we look at wire number 1, we would have that the magnetic field at point A is going to be equal to mu naught I over 2 pi r. R is the radius to that point, the perpendicular radius to that point from the wire, and that's going to be equal to half d. So we're going to have mu naught, 4 pi times 10 to the minus 7, 6 amp current over 2 pi, and then our distance d is going to be 0.35 meters, half of 0.7 meters. And that would be equal to 3.43 microtesla. And as I'm looking at this current coming down like this, if I take my right hand, point in the direction of that current, then at point A, which is to the left of that current, I'm going to be coming out of the page. In other words, the magnetic field is going around like this, and to the left of this current, it's going into the page, and to the right of this current, as you're looking at it, it's coming out of the page towards you. What about wire number 2? I got a current going up, but I'm the same distance away, the same value of the current, so mu naught I over 2 pi r is going to be the same magnitude of the magnetic field, 3.43 microtesla. And as we're going up, anything to the right of this current will be into the page. Everything to the left of this current, as you're looking at it, will be out of the page again. So the contribution from wire number 2 is also out of the page. Hence, our total magnetic field will be the sum of these two magnetic fields superimposed together, one on each other, and that's going to be 6.86 microtesla coming out of the page towards you at point A. What about point C? If I look at the first current, wire number 1 again, with going down like this, at point C, which is to the left, it's going to be coming out of the page, and the distance to it from the wire is going to be 2d, which is 1.4 meters. So our magnetic field will be mu naught I over 2 pi r to point C. Mu naught is 4 pi times 10 to the minus 7. Our current was 6 amps over 2 pi, and our total distance to point C is 1.4 meters. So this is 0.857 microtesla out of the page towards you. What about wire number 2? Current's going up, but we're again to the left of that current, and now, due to that current, the magnetic field is going to be going into the page in the opposite direction. And that would be 4 pi times 10 to the minus 7 times 6 amps over 2 pi. We're only 1d away from wire number 2, so that's 0.7 meters. That's a magnitude of the magnetic field of 1.71 microtesla. into the page. So at point C, we've got two magnetic fields, and they're going in opposite directions. 0.857 microtesla coming out of the page, and 1.71 microtesla going into the page. Which one's going to win? Well, one is going to subtract from the other, and we're going to end up with 0.857 microtesla into the page as we add these fields vectorially, but they're in opposite directions. Take a look at this. Let's say we had two current-carrying wires, and they're traveling in the same direction with the current. What's going to happen? Well, there's actually going to be a force between these wires. Why? Because one wire is producing a magnetic field that the other wire is feeling. For instance, if we look at current I2 going to the right like this, if I use the right-hand rule, my current's going in that direction, there's a magnetic field going around like this, and above this wire is coming out of the page towards you. So that wire number 1 is feeling that magnetic field from wire number 2 that's coming out of the page all the way along the length of the wire. So it's feeling that same magnitude magnetic field coming out of the page all the way along its length. Hence, we know from chapter 29 that there will be a force on that wire. The magnitude of the magnetic field it's feeling is from wire number 2, and that's mu naught I2 over 2 pi d, where d is the distance that we are away from wire number 2. So that'll be the magnitude. The force is going to be ILB sine theta, and I is going to be I1. L is going to be the length of wire number 1, and the magnetic field B is going to be due to wire number 2, mu naught I2 over 2 pi d. Theta is going to be 90 degrees because the current's going this way, the magnetic field's going this way. That's going to be a 90-degree angle between the two. Sine of 90 is 1. So we have this expression down here. Mu naught I2 over 2 pi d, I1 times L. Or I could write this as mu naught I1 times I2 times the length L over 2 pi d, where d is the distance between the wires. What direction will this force be? If the current's going that way and the magnetic field's out of the page towards you, the force on wire number 1 is going to be down towards the other wire. So if these two are carrying currents in the same direction, wire number 1 is going to be attracted to wire number 2. For the same reason, wire number 2, what's going to happen to that? If I have current I1 going to the right, wire number 2 is going to experience a magnetic field from wire number 1 that's going into the page, and with that current going this way and a field going into the page, wire number 2 is going to be attracted upward towards wire number 1. So the two wires are going to be attracted to one another, equal and opposite. The force per length then is going to be equal to mu naught I1 times I2 over 2 pi d, where d is the distance between the wires. It's an attractive force, equal and opposite, if the currents are in the same direction. If the currents were to go in the opposite direction, then we'd have a repulsive force, equal and opposite. So like currents attract and unlike currents repel. Just the opposite of what you had for electric charges. In electric charges, unlike charges attract and like charges repel. Here, like currents attract and unlike currents repel. It's one way that I keep it straight, at least in my mind, is one of the devices that we're going to be interested in is the solenoid. And if you take a core, a cylindrical core, and you take a wire, you can make yourself a solenoid by wrapping a wire turn by turn around this core, and each turn in succession is right next to the last turn. So if you ran a current in that coil of wire, all your currents would go in the same direction through the coils. This device then would naturally have those turns attracted to one another, compacting our device, as opposed to having them repel one another and have it kind of blow up my solenoid. So we think that currents in the same direction will attract. Let's try this out in a problem. Two wires, each having a weight per unit length of 10 to the minus 4 newtons per meter, are strung parallel to one another above the surface of the earth. The top one is being fixed. Their distance of separation is 0.1 meters. What must the current be in each of them for the upper wire to levitate the lower wire? So we're going to fix the upper wire, and we're going to put a lower wire that can move, and we want to levitate it against its own weight. So for that to happen, the magnetic force attracting it up should be equal to the gravitational force pulling it down. And that should be per length of the wire. So we would have that force 2 per length is equal to mu naught I1 I2 over 2 pi d. I1 and I2 are the same current I, and that should equal the weight per length of wire number 2 in order to keep it in equilibrium. Putting our numbers in, mu naught is 4 pi times 10 to the minus 7. Our currents are going to be the same, so we're going to have I squared over 2 pi. We are 10 centimeters away, 0.1 meters away, and our weight per length was 10 to the minus 4 newtons per meter. So I can solve this for I, and if I do, algebraically, I get that my current would be 7.1 amps. So if I ran 7.1 amps in each of these currents, then the lower wire would levitate against its own weight. How about that? If I had a little bit, it's an unstable levitation, it's an unstable equilibrium. If I give it a little bit of a push upward, then the magnetic force would be stronger than the gravitational force at that moment, and it'll continue to go upward as it goes towards wire number 1. If I were to give it a little bit of a push downward, then the gravitational force would be greater than the magnetic force as we move further away, and hence it will fall. So it's a very unstable equilibrium. I could do better if I actually had my fixed wire on the bottom and had a wire sitting on it from top and in equilibrium by repulsion that way. That would be a more stable equilibrium. I could push it one way or the other, and it would pretty much stay near that point. Well, we want to use Ampere's law for more things than just infinitely long wires. And one question you might have already is, how often are we going to be dealing with infinitely long wires? That's a good question. In terms of problems, quite a lot. In terms of the real world, well, we don't usually have infinitely long wires. But if I had a wire and I was pretty close to the wire, then as far as my perspective is concerned, the wire is looking pretty infinite to me. So in cases where you're relatively close to some wire segment, then the Ampere's law and the formula for infinitely long wire is a very, very good approximation for the magnetic field at that point. So here's another situation. Consider this. Let's say we have a current loop, and the current's going around in this circle. And if you consider a section of this current loop, say this bottom section down here, if I were to use the right-hand rule for that bottom section, pointing my thumb in the direction of the current, then my fingers would indicate a magnetic field coming out of the page towards you above that section. As I start to go around counterclockwise around this circle, I would still be coming out of the page for every little section of current that I'm considering around this loop. So as I go around with the right-hand rule, I'm coming out of the page for every little section. It's got to be right-hand rule, so it's kind of hard for me to indicate here. Even coming down on this side, I'm coming out of the page towards you. So as I go around this loop, every little section of this loop is going to contribute in the same direction to a magnetic field coming out of the page towards you if I'm going counterclockwise in current around this loop. For the same manner, I could use that other form of the right-hand rule, which we're going to talk about more and more in the future. But for a current loop like this, if I actually curl my fingers in the direction of the current loop, my thumb points in the direction of the magnetic field through the center of this loop. So really the loop intensifies, and I have myself a situation where I have a loop, magnetic field going definitely in one direction, this way, and it's almost like a little magnet. You know, if I think of it, I got a magnet, I got a north pole and a south pole. North pole where the lines are coming out, and then coming in to the south pole. It's a little magnet. This current loop is a magnet, kind of like a bar magnet. If we had a bar magnet with a north and south pole, the magnetic field lines would come out of the north pole and then go into the south pole. In fact, the lines never really end. They form closed loops. So the lines come out of the north pole, come into the south pole, and go through the material as they close the circular loops. So a little current loop is like a little magnet. How about that? And if I were to add loop after loop after loop of current loops, I can intensify that little magnet and make it stronger and stronger proportionally. That's the idea behind a solenoid. Here's an example where we got loop after loop after loop, and we're looking at a cross-sectional area of our construction here, our solenoid, and you have your current coming out of the page towards you on top and into the page away from you on the bottom. The result, though, is a magnetic field going to the right as you're looking at it. The magnetic field in the center of this device, this solenoid, is equal to mu naught, the magnetic permeability of free space, times little n, which is the number of turns per length, times the current that's going through the loop in the solenoid. Mu naught little n I, where little n is the number of turns per length for the solenoid. So how many turns you have per length of the solenoid is little n. Right-hand rule, curl your fingers in the direction of the current through the loops. Your thumb points in the direction of the magnetic field through the solenoid. So it's like what you would do for one loop, but now you have many loops, all with currents in the same direction. The magnetic field is in the direction through the center of the solenoid, like that. Here's a proof using Amperes' law. Consider a closed path where one side of this rectangle goes through the center of the solenoid. That's this side right here. And then we have two perpendicular sides that go up. And then I have a fourth side way above that could be arbitrarily far away. It could be infinitely far away. And I'm going to apply Amperes' law to this closed loop, this square loop. So we're going to apply B dot ds over this square loop that we've constructed. It should be equal to mu naught times the total current enclosed by this path. Well, in the first part of the path, I got the magnetic field going like this, and my ds is going in the same direction for a length L. So that's going to be B times L for B dot ds there. But as I'm coming out of the solenoid, the magnetic field is going this way, and my path is going this way as far as my square path is going. There's going to be an angle of 90 degrees there. Cosine of 90 is 0. So this B perpendicular width here is going to be a 0 term. And for that matter, on the other side as well, where the magnetic field is going this way and our ds is going this way, it's going to be a 90-degree angle between them. That's going to be 0. And then for the side on the top, we're arbitrarily as far away as we wish to be, and hence the magnetic field at that location is going to be 0. So even though it might be anti-parallel at that point, giving us a finite dot product, the magnetic field itself is infinitely far away, so that is 0 as well. So 3 of these terms are 0, and we end up with just BL is equal to mu naught times the total current enclosed in our square. That's not just one I, that is Ni, how many I's that we have in all these loops. So we have N of those I's going through our square, and that's why we have our total current enclosed is N times I. So our magnetic field will be equal to mu naught, number of turns, divide by the length of the solenoid times I, or mu naught little n I. That is the magnetic field through the center of a solenoid, and a very simple proof using Ampere's law. If I did not have free space in the center of the solenoid, instead of mu naught, if I put some kind of material in there that had its own magnetic permeability, then I would replace mu naught with mu, whatever mu was for that material that I put in the center of the solenoid. So that's why if you took a nail and you wrapped a wire around the nail, you would make yourself a very good electromagnet, because the magnetic field would be mu little ni, depending on the number of turns you had and the current you run, and the mu would be from the steel of the nail that you put in as your core, and that would greatly increase the magnetic field through the center of that solenoid device. Alright, so we're going to conclude this chapter 30 with a brief discussion of magnetic flux. We can say that magnetic flux, which is the number of field lines that actually go through an area, is analogous to what we have discussed earlier about electric flux, where we had an electric field going through an area. Flux is flux. It's the number of field lines that go through a given area. So we define magnetic flux, at least in an integral sense, as the integral of B dot dA, where A is the perpendicular area vector for a surface. If we add up all that contribution of what goes through a surface, that would be the flux through that surface. For a planar area, making an angle theta with a magnetic field, the flux through that area would be the field B times the area A times the cosine of the angle between their two directions. That would be the flux through a planar area. If the angle were 90 degrees, cosine 90 would be 0, and the flux lines would never go through that area, so you would have no flux through that area. The unit of flux is the Tesla meter squared, and it comes up so often in magnetics that we actually have a name for that, and that is the Weber. So the Weber, WB, is the Tesla meter squared. The net magnetic flux through any closed surface is always 0. This is Gauss's law in magnetism. And basically, it's a statement that's saying that there's no such thing that we can find in a macroscopic sense being a magnetic monopole. Because if you had a north pole somewhere, you're always going to have a south pole right there. You can't isolate a north pole by itself or a south pole by itself, because in reality the magnetic flux lines are closed loops. So anytime you have a north pole, you're going to have a south pole right there going in because it's a closed magnetic loop. So I can't take a closed three-dimensional surface and enclose something where the flux is only coming out, because for everything coming out of that surface there will be flux lines going in. Hence, the net magnetic flux through any closed surface will always be 0, and we can't enclose any flux producing device by itself inside that closed surface, unlike what we had with the electric flux, because we could always put a charge inside a closed surface, and so in that case Gauss's law was the integration of the E field with the area was equal to 1 over epsilon naught times the charge enclosed. We could do that because we could actually enclose a flux producing device. We can't do it with magnetism. So there are no magnetic monopoles. A source of magnetic flux cannot be enclosed in a surface. So review, we have Ampere's law. The integration of a magnetic field around a closed path is proportional to the current enclosed by that path. Mu naught is the magnetic permeability of free space, 4 pi times 10 minus 7. For a long wire, the magnetic field by Ampere's law is mu naught I over 2 pi r, where r is your distance away from the wire. For a solenoid, the magnetic field through the center of the solenoid is mu naught little n I, where little n is the number of turns per length. That concludes chapter 30, and we're going to be using this idea of magnetic flux to help us in our discussion of power generation and electric field in the next few chapters.